So this is it's a great pleasure to have Robert Andrews here for a hybrid meeting with Bark, with Meow, and with the whole internet attending. And without further ado, Robert, please.
All right. Well, thank you all. Thanks for coming. Thanks for having me here. So I want to tell you about some recent work about matrix multiplication and polynomial identity testing, and a new relationship between these two problems. So I want to start the talk by just reminding you all what is matrix multiplication, maybe not remind, but actually tell you what is polynomial identity testing, and then I'll tell you about the relationship between these two. And if you have any questions, feel free to stop me at any time, just ask. There should be plenty of time for questions during the first part of the talk. Okay, so matrix multiplication, this is something we're all very familiar with, right? This is a problem where I give you two n by n matrices, and I ask you just compute their matrix product. Right, so I'm giving you these two matrices. I ask you to output the product. And the natural question here is, well, how much time, how many arithmetic operations do we need in order to actually compute this matrix product? And here I'm talking about matrices over the complex numbers because I want to emphasize that my perspective is I'm just counting arithmetic operations. I'm not concerned with bit complexity. I don't actually want to write down the entries. I'm just counting additions and multiplications. Okay. So obviously, we'd like to know how many operations are necessary or sufficient for this problem. And usually we measure progress on matrix multiplication by this exponent omega, which has maybe a bit of a weird definition if you haven't seen it before. So we're looking at all real numbers tau, such that you can compute this matrix product in order n to the tau arithmetic operations. And then we take the infimum of all these tau. So for example, if omega is 2, maybe there's not an n squared time algorithm, but you can get n to the 2 plus epsilon for any epsilon. Okay, so we measure progress on designing matrix multiplication algorithms in somewhat of a coarse sense using this omega. This is in some sense ignoring these subpolynomial factors in the complexity. So what do we know about omega? What do we know about matrix multiplication? Well, we have some bounds on it. So the obvious bounds are it's between 2 and 3. You need at least, it should be at least 2 because you need to write down the output. And it's at most 3 because you can just use the definition of matrix multiplication. And that gives you an n cubed time algorithm. But we know more things about this. So the first result on this is Strawson's well-known paper from about 50 years ago, where he showed that omega is strictly less than 3. Right? And he designed some very clever algorithm for 2 by 2 matrix multiplication. And then through recursion, you can lower the bound on omega to about 2.81. And then there have been more and more and more and more works pushing the upper bound further and further down. And I'm ignoring, this is not a full list of works on matrix multiplication. This is just some key points along the way where the exponent dropped even further. And right now, the world record sits at about this 2.372 and some change by Allman and Vasilevska-Williams from just a few years ago. So, this is all nice. This gives us a lot of nice problems to work on. We can attract some funding with this, but why should we care? Well, okay, matrix multiplication is a fundamental problem, so we should care about it just for that reason alone. But it has nice applications as well. So it governs the complexity of a lot of nice problems in linear algebra, such as computing the determinant, solving linear systems and linear programs. You can use this to compute QR decompositions or LUP decompositions of matrices. You can compute the characteristic polynomial of a matrix. Lots of nice linear algebraic problems, but you can also do things that don't look like linear algebra on their face. So for example, you can find k-cliques in a graph using fast matrix multiplication. This isn't something that's obviously linear algebra. You can also recognize strings in context-free languages, again, using fast matrix multiplication. And there are a lot of other applications of this. And I think the easiest way to demonstrate this is I looked, and according to Google Scholar, this paper, the most recent upper bound has been cited about 200 times in the past 2 years. So clearly, people care about this. This is a problem that's worth studying. And we'd like to understand its complexity. And the major open question here is omega equal to 2? Now, some people conjecture yes. Maybe you're not so sure about this. I don't really know what I believe. I don't think I understand this problem well enough to have an opinion. But nevertheless, this is a major open question that faces us in algorithm design. That's matrix multiplication. question here is omega equal to 2? Keep that in mind. We're going to shift over to a different problem, which is polynomial identity testing. So what's polynomial identity testing? I give you some polynomial over a field. It's a multivariate polynomial. And I ask you, is it in fact the 0 polynomial? Okay. Now, if I give you this polynomial just as a list of coefficients, this is a really easy problem to solve. You just check that all the coefficients are 0, right? So that's not interesting. But it is interesting if I give you the polynomial in a more succinct fashion. So I'm going to give it to you as an algebraic circuit. I'm going to give you a recipe for computing the polynomial. So for example, this circuit, it takes as inputs 2 formal variables, x and y, and it computes the polynomial x squared minus y squared. So here I'm really thinking about this polynomial as a syntactic object, not thinking about it as a function. It's really this formal sum of monomials. I give you a circuit and I want to know if it's computing 0 or if it's computing something that isn't 0. Now, there are 2 points that I want to make, that I want to emphasize about this. The first is that you can do something with this representation. You can evaluate the circuit. So you can take this polynomial, query it at some points, and see what kinds of evaluations you get. So you can do something, but you can't just take the circuit and write the polynomial as a sum of monomials. Doing that will take exponential time in the worst case. So you can maybe do something, but there aren't, you can't do this just trivial algorithm where you expand out the polynomial. Okay. So maybe this is a bit of an abstract definition. Let me give you a more concrete example of this problem. So I'm going to give you a polynomial, and I'm going to ask you if it's 0. And in this example, just for context here, this I is the square root of -1. So here's my polynomial. Is this 0? I don't know about you, but I can't figure anything out just by looking at this, right? I can't find any obvious structure that says, oh, this polynomial is definitely 0, right? It's this weird sum of 3 terms, each of which is a product of 4 things. And well, if I were to expand this out by hand, that would be somewhat painful. And I could check if everything cancels, but I don't want to do that. And you probably don't want to do that by hand either. You could make some substitutions and evaluate this. And certainly if you get a non-zero evaluation, then you know the polynomial is not 0. But if you plug in numbers and you keep seeing 0, how do you know when to stop? If you get really bored during this talk, here's a puzzle for you. Tell me if this is 0 or not. And if you're really curious, I can tell you at the end what the answer is. But you might say to me, well, this is kind of uninteresting. This is just some random expression you picked out of thin air. Like, why should I care about this? Well, here's another example. So here's a determinant. It's a 5 by 5 matrix. I zeroed out most of the entries, but there are 10 non-zero entries that are all variables, right? So this A through J, these are formal variables. And I want to know if this determinant as a polynomial, is it 0 or is it non-zero? Now, it turns out the answer is no, it's not 0. And if you think for a little while, you can probably figure out a term that's going to survive when you expand out the determinant. But again, why should you care about these random determinants? Well, here's a different question. Here's a graph. Does it have a perfect matching? Now, again, if you stare at it for a while, you probably can find a perfect matching hidden somewhere in there. I know there's one. I put one in there, but I don't remember where it is. But the point is, there is a perfect matching in this graph. And now, why am I asking both of these questions? Well, it turns out these answers are highly correlated. This determinant is non-zero because there is a perfect matching in this graph. And vice versa, if there wasn't a perfect matching in this graph, then this determinant would be 0. So just by testing whether or not a determinant of some matrix is 0 or non-zero, we can test for perfect matchings. Okay. Now, the punchline here is that it turns out you can test if this determinant is 0 quickly in parallel, but it's a randomized algorithm. Okay, but what does that mean? You get a randomized parallel algorithm for testing if a graph has a perfect matching. Now, in the previous slide, this construction was for bipartite graphs, but there's an analogous construction that works for non-bipartite graphs. So this is one application of PIT. You can test for perfect matchings and you can test in parallel, but it's randomized. That's a caveat. Another application is testing if a number is prime. Right? There's this very well-known primality testing algorithm of Agrawal, Kyle, and Saxena from early 2000s that tests for primality in deterministic polynomial time. How is that algorithm designed? They took some particular instance of PIT and they developed an efficient deterministic algorithm for it. can also use this for algebra problems, which seems to make sense. You can test if one polynomial divides another. You can use this to factor multivariate polynomials. This is also used in various results in complexity theory, like the proof of IP equals P space. Because when you're designing an interactive protocol for this quantified Boolean formula problem, there's this sum check that you're using to verify the prover's claim of whether or not this thing is satisfiable. And that sum check protocol is using PIT in a useful way. There are other applications. So there are these objects called read once branching programs. Never mind exactly what they are. They're some non-uniform model of computation. And the point is, if I give you two of these, it's not obvious whether or not they might compute the same function, but it turns out you can test if they compute the same function using polynomial identity testing. And I should mention, we believe you can't test if two circuits are equivalent, right? This would be an instance of SAT. So there's something special going on here. And there are other applications as well. One that I think is kind of fun is there's a notion of these multi-dimensional compressed strings, where it's in 2D, a compressed string is either a single character or it's two compressed, the compressed strings are like rectangles of characters. And I can either glue two rectangles of the same height horizontally, or I can glue two rectangles of the same width vertically. And then I want to test, are these highly compressed strings equal? You can do this with polynomial identity testing as well. So this is a useful problem to solve because we can use it to solve many other different problems. It's a useful tool in your algorithmic toolbox. So how do you solve it? Well, I told you there's a randomized algorithm for it. Let me tell you what that is. So it's very simple. 3 steps. First step, you're going to pick a subset of your field, and the size of that subset should be about twice the degree of the polynomial you're testing. Okay, so a priori, I need to at least know something about the degree of the polynomial. You need to promise me that its degree is at most some number. Otherwise, I'm not going to test it very efficiently. Then what you're going to do is you're going to sample a point at random whose coordinates lie in this subset. And now you evaluate your polynomial at this randomly sampled point. And you say the polynomial is 0 exactly when the evaluation is 0. Okay. Now, if the polynomial is 0, you always get a 0 evaluation. You always say correctly that the polynomial is 0. What's the failure mode here? The failure mode is if the polynomial is non-zero, but you might have seen a 0 evaluation. So does that happen very often? And it turns out no. So there's this well-known Schwartz-Zippel lemma that says the error probability of this algorithm is not too large. So if I have some polynomial that's not 0, and I do this sampling, the probability that I get a 0 evaluation, that this algorithm is incorrect, is at most the degree of the polynomial divided by the size of the set. So for the choice of parameters here, I get an error probability of at most 1/2. Right? This is nice one-sided error, and of course you can drive this down to a very small error by repeatedly sampling different points, testing them all. It's a very nice algorithm, very fast too. Right? You just evaluate at one point.
Is there a reason that you're sampling from a fixed test rather than all of the field?
Well, so if I'm working over a field like the complex numbers, then I don't really know how to sample a random complex number.
Oh, okay.
Right.
Okay, that's the only thing.
Right, right. So I do.
Choose any distribution over the complex numbers and sample from that.
Yeah. So any distribution that
is sufficiently uniform.
So as long as sets of codimension 1 and larger have 0 measure under your probability distribution, or very small.
That is simple. This is simple.
Yes. This is simple. But also the point is, like, at the end of the day, you do want to run this on a Turing machine, right? So I'm thinking about all of this with arbitrary complex numbers, transcendental numbers, what have you. But if you want to run this on a Turing machine, you do need to sample from something finite. And the point is, if the degree is like polynomial in the number of input variables, the set's not too large. You can do this sampling.
But if I am in some, small field and a super high degree polynomial, but then I can go to an extension field.
Exactly. Go to some large enough extension field. Right. So the polynomial might be defined over like F2 or F3, but I'm going to, my algorithm will work over some extension of that field. Okay. So here's a randomized algorithm. Natural question is, can we de-randomize it, right? That's sort of the obvious thing here. Can we design an efficient deterministic algorithm for PIT? Now, this would be interesting algorithmically because we would, for example, get a deterministic parallel algorithm for perfect matching. That seems like a nice thing to get. But it also turns out this is closely connected to proving lower bounds for algebraic circuits. So there's a line of work starting with Cabanetton and Pagliazzo from the early 2000s that says, if I can prove lower bounds for algebraic circuits, then I can de-randomize polynomial identity testing. So given a lower bound, I can do something deterministic. And there's an implication in the other direction that if I can de-randomize PIT, then you can prove new circuit lower bounds for that with that algorithm. Now, these new lower bounds would not necessarily be for the permanent, but they're certainly beyond what we know how to prove right now. Okay, so there's not only an interest in this from an algorithmic perspective, but there's nice complexity questions that are arising here as well. It's tightly connected to lower bounds, right? And we all want to prove lower bounds. Right. So I should also say that, for very restricted classes of circuits, we do actually have lower bounds. And sometimes we can take those lower bounds and turn them into algorithms for PIT. And sometimes this is a very direct thing. Sometimes we use some intuition or some information that we learn about that circuit class from the lower bound. The lower bound tells us some weakness of the circuit class. We can use that to design an identity testing algorithm. So the point is we do have some knowledge for these restricted models of computation, like these so-called read-once branching programs or low-depth circuits. We can do something interesting there, but we haven't designed fully polynomial time algorithms. Those are still outside of our reach. So we want to de-randomize this. Open question number 2. Is PIT solvable in deterministic polynomial time? That's the second question that I want you to think of. Okay. So we saw there's an open question about matrix multiplication, open question about polynomial identity testing. So let's think about the possible worlds that we could maybe live in. All right. So I'm going to measure the world in 2 dimensions, and they're the most important dimensions of our world. One is the value of omega, and well, it could either be 2 or larger than 2. And the second most important fact about our world is the time complexity of PIT. And here I'm just going to restrict it a little bit. I'm looking at circuits of linear size. All right, so this is a very, this is the first case of PIT that you would hope to solve, is I give you a circuit of just linear size, and I ask you to test if it's 0 or non-zero. All right, and I'm going to distinguish between 3 different cases. The first case is, maybe you can solve this problem in polynomial time. The second is, well, maybe polynomial time is outside of our reach, but you can at least do it in sub-exponential time. And the third really sad possibility is that it requires truly exponential time, that you cannot de-randomize this at all, even for these very, very small circuits. Now, of course, we popularly conjecture that we live in this top left box, right? We think probably omega is 2, and we really think that PIT can be solved in polynomial time. But a priori, we could live anywhere in these 6 boxes. And I should mention, of course, there are finer gradations of running time that you could expect for PIT, and there are finer gradations of the value of omega. But the point is, we could be really, really sad and live over here, where omega is larger than 2 and you can't do anything for PIT. The main result of this work is to tell you we don't live there. All right. So at the very least, we can rule out a very, very sad world where you don't have fast matrix multiplication and you can do nothing for PIT. So let me tell you in a little bit more detail what this result says. All right. So I'm going to state it in 2 ways. First, I'm going to state it as a win-win kind of result. So the win-win result here is there are 2 statements, at least one of them is true, and it's what I said on the previous slide. Either omega is 2, or this one's a little more detailed. There are positive constants, epsilon and delta, so that you can test circuits of size n to the 1 plus delta in time exponential in n to the 1 minus epsilon. So for circuits that are a little larger than linear size, you can make a little bit more progress than brute force. Okay. And to calibrate your expectations here for number 2, the naive algorithm would run in time exponential in n log n. Okay. So at least one of these things is true. We think both of them are true, and we think something much stronger than the second item is true, but we don't know how to prove any of these unconditionally. But one of them is true. Let me state it in a different way, which is a sort of hardness to randomness there, right? In this previous slide, I said one of these is true. So equivalently, I could say not one implies two. So how did we say it like that? Well, let's say I have some circuit that has S multiplication gates, doesn't compute a polynomial of very large degree. Then you can test if that circuit is zero deterministically in this running time, something exponential in n to the 1/2 times s to the 1 over omega times log n, and then you add an extra s term because you actually need to evaluate the circuit. Right? Yes.
Why is the degree coming into the picture? Seems a bit sudden.
I just want to bring up the degree because I want to use short zipple and then derandomize that. And if the degree is far too large, then
so it's an explicit derandomization of short zipple somehow.
Yeah. I mean, it's going to be a hitting set generator, and then I use short zipple with that. I'll go into this more in a couple of slides. But I need to state something about the degree so that I can actually state this very explicit time bound. And what you should notice here is, well, if you think of S as n, right? This is this quantity here is square root of n times square root of n, at least given our knowledge. But if omega is larger than 2, and S is n, then this is something far smaller than n, right? But maybe you think omega is 2. And so I'm just here selling you a theorem that says false implies result. And that's not interesting. So it turns out there's a bit of a more fine-grained view you can take on this result. And it's in terms of this quantity, this thing that's this underline R of S, but inverse. And this underline of R is this so-called border rank of matrix multiplication. Now, I don't want to precisely define it. Intuitively, it's the number of scalar multiplications you need in order to compute a matrix product. All right. And why is this an interesting quantity? Well, it turns out that the matrix multiplication exponent captures up to sub-polynomial factors. It captures this border rank thing. Okay. But it could be the case that the border rank is something like n squared times a very large polylogarithmic factor. All right. If that's the case, omega is 2, but you still get some kind of non-trivial algorithm. All right. And I more strongly believe that this is something larger than quadratic in n. We don't know how to prove that even, but you should be able to prove a lower bound for this quantity at least. Maybe omega is 2, but you can still do something here. All right. So that's the statement of the result. I want to say a few more remarks about this. So the first is, what can we say unconditionally? So, So what can we say about unconditional results on PIT? So the best lower bound we know on this border rank quantity is about 2 times n squared, and this is only from a few years ago. Okay. Now, if you plug this into the previous slide, you get the following unconditional result, that you can test a circuit with S multiplication gates in time exponential in the geometric mean of n and s. Okay, now if s and n are equal, this is doing nothing interesting. But if you have a sublinear number of multiplication gates, you get an interesting result. And it turns out that that is an interesting regime to study, because even though I might have a sublinear number of multiplication gates, my circuit can still read the whole input. So the circuit can still compute something non-trivial. And as far as I know, this is the best unconditional de-randomization of PIT for general circuits. Now you might ask, well, these parameters are pretty bad. Like, yes?
Sorry to ask a similar question again, but I mean, is there a dependence on D now? Because I'm kind of getting lost with
Yes. So there should be a dependence on D here. I'm implicitly assuming that it's
D is
degree is polynomial in n, yes.
Okay.
Yes.
Okay.
Sorry about that.
Yeah.
So you might ask, can we do better than this?
Obviously.
Oh.
We lost the slide.
Oh.
Thanks.
no.
It's back.
Okay.
Yes.
Okay. All right, so can you do something better? Right, so it turns out you can work out the constants here, and as long as S is less than about n over 192, you get some non-trivial algorithm. Now you might ask, well, can you do better? Can you get better parameters? Could you let S be larger and still get some kind of non-trivial algorithm for PIT? And it turns out you probably can't, right? At least not by much. So why is this? So let me tell you the best lower bound we know for algebraic circuits. And this is almost 40 years old. So Bauer and Strassens showed that if you want to compute the sum of the nth powers of n different variables, this requires at least n log n multiplications. And you should know that this is also sufficient because I can compute these nth powers by repeated squaring and then add them up. Okay? So this is the best lower bound we have for general circuits. And the claim is, if you can do PIT where S is much larger, asymptotically larger than n log n, then you would improve on this lower bound. All right? And this lower bound, this has been open for 40 years to improve on this. And I like to think of myself as optimistic, but not optimistic enough to improve on this. So the point is, you get something non-trivial here, but you can't improve on it by much without running into this big challenge. Okay, so there's a little room for improvement, not too much. Okay, so maybe before I move on, just any questions about the statement of the results, or what's going on here? Okay, so I want to take some time to tell you at a high level how a proof of something like this works. Okay, and to tell, yes.
Maybe just one question. So you said brute force is exponential in n log n.
Yeah.
For the
Yeah, let me go back.
T.
This.
Yeah, could you just quickly say how that is?
Yeah. So right. So again, I'm making the implicit assumption that you have polynomial degree.
Yeah.
And so short zipple runs in something like degree to the n.
Yep.
Degree is polynomial, so it's like n to the order n.
And the delta doesn't come in at all. The size of the circuit will not matter.
Well, the size of the circuit, you would get some like n to the 1 plus delta factor out here.
Okay. Yeah.
So that is also captured by the log n.
Okay.
Yeah.
Yeah.
Okay. All right. So let me tell you a little bit about how a result like this gets proven. What are the objects at play here? So, okay. So we're going to construct an object called a hitting set generator. And if you're familiar with pseudorandomness, this is analogous to hitting set generators or pseudorandom generators from the Boolean world. Okay, so here's the setup. So we've got some curly C is a set of polynomials. All right, and you can think of these as polynomials that can be efficiently computed. And these are the ones that we want to test. So a hitting set generator, it's going to be some map that takes L variables to N variables, and it's a polynomial map, meaning that every coordinate of the output is a polynomial function in the inputs. Okay? And we're going to say this is a hitting set generator for curly C if the following result happens. Take some polynomial in curly C. If that polynomial is non-zero, then when you compose it with the generator, it remains non-zero. So what is this doing? This is some kind of variable reduction. I'm reducing the number of variables while preserving non-zeroness. Now, preserving zeroness is easy. That's always going to happen, right? The difficult part is preserving non-zeroness. And these generators are ways to reduce the number of variables while you preserve non-zeroness of the polynomial. And there are two parameters that are interesting about these things. So the first is the seed length, which is just the number of input variables to the generator. And the second is the degree of the generator, which is just the maximum degree of its outputs. And our goal is to design generators that have small seed length and degree that's not too bad. And also you should be able to evaluate the generator quickly. Right, so this is the kind of object that we're going to look at to design algorithms for PIT. Now, how can you use this for PIT? So let me show you. So the first algorithm that you might consider, the first deterministic algorithm you might consider for PIT is you test the polynomial by brute force. Okay, now how many evaluations do you need to do that? Well, if you look at the parameters of the Schwarz-Zippel lemma, the number the number of evaluations you need is something like degree plus 1 to the n. All right, so it's exponential in the number of variables. Okay, what's the second algorithm that you might consider? Well, if I have this generator, what I can do is I can take my polynomial, compose it with the generator, and then test if that composition is 0. Okay, and I can do this by brute force. Now, how many evaluations does this take? Well, now it's degree of the composition, which is degree of f times degree of generator, plus 1, raised to the seed length, L, the number of input variables to the generator. And so what you should see is that if the generator has small degree and L is noticeably smaller than n, I've made a big improvement. Right? I went from something exponential in n to exponential in L, and the hope is that L is going to be smaller. Right? So this is sort of the recipe for taking these hitting set generators and converting them into algorithms for PIT. So I only want to talk about generators at this point. It's just enough to construct this generator, and then you follow this recipe, you'll get the algorithm. So the interesting part is building the generator. So let's try to prove this and see what happens. Okay. So first attempt is, let's just assume omega is 2.1. We've got some lower bound. Now, 2.1 is a bit arbitrary, 2 plus epsilon is fine, but I just want to make the numbers explicit. So the first thing is that assuming a lower bound for matrix product, this is a task where you compute many different output polynomials, right? I have an n by n output matrix, and I want to compute all n squared entries. And I have a lower bound for that. It would be nice if instead I had a lower bound for a single problem. And so there's a way to do that. So in this same paper by Bauer and Strassen, they showed that if you have a lower bound for matrix product, then the same lower bound applies to this polynomial here, this trace of a product of 3 matrices. So I take x times y times z. These are all n by n matrices of variables, and I take the trace, where the trace is just, I sum the diagonal entries. Okay. Now it turns out that a lower bound on matrix multiplication implies a lower bound for this trace polynomial. Okay. So now I've got a single hard polynomial. And what I'd like to do is I'd like to use hardness versus randomness, right? These theorems that say a lower bound implies a derandomization. So we're working with circuits. So this has been studied already in this work I mentioned by Cabinetson and Pagliazzo. So here's, if you sat down to prove this, here's what you would try to do. Okay. So using this Cabinetson and Pagliazzo result, you would build a generator, all right, out of this hard polynomial, this trace of matrix product. And what you get is that if some polynomial f composed with the generator is 0, if the generator fails, then you can take a circuit for f and use it to reconstruct a circuit that computes this trace polynomial. Now, why is this interesting? Well, if f was computed by a very small circuit, this modification is efficient, right? It's going to only blow up the circuit size of f by a small amount. And so what you would like to do is you would like to say, okay, suppose f is efficiently computable, and suppose the generator fails on f. I'm going to construct a new circuit for this trace of matrix product, that is actually so efficient that I will contradict my lower bound. So the generator could not have failed in the first place. So that's what you would like to do. But the problem is, well, this reconstruction procedure, it blows up the circuit size by a polynomial factor. And that's too much to deal with here because our lower bound is so tiny, right? This is an n to the 2.1 lower bound, but your number of inputs is n squared. So it's really like number of inputs to the 1.05. It's a tiny, tiny lower bound. So there's too much blow up incurred in these traditional hardness randomness type results to actually prove what we're trying to prove, right? That's where things go wrong. So let's try again, but we're going to do a sort of what I'll call a white box hardness versus randomness. And the reason it's white box is I know the polynomial that's hard. I know the hard polynomial. I can do something with that. So here's the generator we're going to look at. Okay, so we're trying to hit a circuit with n variables. So I want, instead of thinking of the circuit as having n variables, I want to think of it as having a root n by root n matrix as its input. Okay, and now here's the generator that I'm going to use. I take a root n by r matrix and another r by root n matrix, as my inputs to the generator, and the generator outputs their matrix product. That's the generator. Now, of course, R is a parameter that we're going to pick. And what you should think of here is the seed length of this generator. This is something like 2 times square root n times R. So if I can pick R noticeably less than square root n, I'm going to make some progress, right? Because then n square root n times R is like much less than n. Okay. So why am I picking this generator? It's because I know something about the polynomials on which this generator fails. All right, I know something very explicit about them. So here's the fact that I don't want to prove, but just believe me on this. If I have some polynomial f that vanishes on the output of this generator, well, it turns out that I can write this polynomial as this somewhat weird looking sum. So let's step through this. I'm summing over subsets s and t, which are subsets of the integers 1 through n, and these are both sets of size r. Now, what's the s comma t entry of this sum? Well, I take this matrix X of variables, I look at the rows indexed by s and the columns indexed by t, and I take the determinant of that submatrix, and then I multiply it by some other polynomial. Okay, and this could be some arbitrary polynomial, but I just know that this entire sum is not going to be 0. Okay, so I know something about the polynomials that fail on this generator. I know exactly what they look like. There's a large number of them. Okay, and what we'd like to do, we'd like to say that, if I have a lower bound for matrix product, then I can prove a lower bound for all of these polynomials. What would that mean? That would mean if I have a small circuit, it cannot be computing one of these. So in fact, the generator hits that circuit. Right? So all I'm saying is all the bad examples are not computed by small circuits. That's what we want to prove. And the intuition here is, well, there's a lot of big old determinants here. And earlier I said that matrix product and computing the determinant are very closely related. So if I have I'm starting with a lower bound for matrix product. So that should say something about a lower bound for determinant, but now I've got this very weird sum of products that involve determinants. So maybe things are a little weird. But I claim we're still going to prove a lower bound for all of these polynomials. Okay, so let me map out what the proof looks like. So we're going to try to lift this lower bound from matrix product to all these weird polynomials that could destroy our generator. Right? So here's the outline again. So we're starting with the assumption that omega is larger than 2. And I'm just going to say it's 2.1. So again, we use this Bauer-Strassen result to say, okay, this trace of matrix product, it requires large circuits. And I'm actually going to be a little more careful here. Instead of saying it requires circuit size, which is, number of variables to the 2.1, I'm going to count the number of multiplications. Okay, and I'll say why in a minute. I should also mention I'm changing the parameters around a little bit here just to make things match nicely. So these are matrices of size r over 4 by r over 4. This is the same r from the previous slide. Okay. So what we need to do is we need to show that all these polynomials vanishing on our generator require like r to the 2.1 multiplications. Now, how are we going to do that? Because these are very unstructured polynomials. Well, in some joint work with my advisor, we already studied these polynomials, and we managed to prove a bit of a normal form for them. So if you want to prove a lower bound for all of these polynomials, it suffices to prove lower bounds for polynomials like this. So what are these? I have a product of determinants. Every determinant in this product comes from the upper left corner of the matrix. Right? So I'm taking the first I rows and the first I columns. And then I'm raising that determinant to some power. Right? So I have a large product of powers of determinants. But I do know that there is at least one determinant here of size r by r. Okay, so there's a large determinant, but there could be maybe some smaller determinants, maybe some medium-sized determinants, weird things. But all I need to do is actually just prove a lower bound for this. All right, and then hit it with this hammer and says, you can actually get this lower bound for all the polynomials that the generator fails to hit. And so that's what this work does, is it shows how to go from this trace of matrix product to a lower bound for this trace of matrix product to a lower bound for the polynomials that look like this, that look like these products of determinants of the upper left submatrices, where you've got at least one large determinant. Okay. So that's all I want to say about the proof sketch. So any questions about that? Yeah.
The hardness really comes from this one R by R determinant?
Yeah, that's exactly where it comes from. Yeah.
So the other stuff is noise.
Yeah, but you still need to deal with it because like you need to rule out that maybe if I take an R by R determinant and multiply it by some other determinants, maybe that's easy to compute for some reason. Like maybe it's easier, right? And part of the difficulty here is we're dealing with a really delicate lower bound, right? We know, for example, there are these results that say you can factor algebraic circuits efficiently, right? So if I give you a circuit that computes this product, I can pull out a small circuit that computes an R by R determinant. But the problem is that factoring procedure is going to blow up the circuit size too much. So we're really working where like the reductions that we're giving have to be very aggressive with the parameters. They're essentially like linear time reductions, so to speak.
So you're trying to put a large trace of them?
Yes. So I'm going to somehow substitute the variables here to pull out that large trace, but you need to do it in a clever way because you need to, you know, if there was one determinant here and it was size R by R, that's not too difficult. You've got these powers, you've got many smaller and medium-sized determinants, so somehow everything needs to work out nicely. Yeah. Yeah. So I'll say that this is what's going to be in the second, more technical half of the talk. Okay, so if you're interested in how this works, stick around. So other questions on this?
I have one question. So there's an obvious upper bound and f of x, which is like n choose r or something, but is there like a better upper bound for f of x?
So in terms of upper bounds, so let me just get this expression here. Right, so
I kind of find it believable that this polynomial is hard.
right.
It could be quite hard.
Right.
So,
Well, okay, so these FSTs, these are arbitrary.
yeah,
So I could pick like the permanent,
exactly.
right? And that would make this super difficult to compute,
Yeah.
right? But it could be that there's some way to pick these in a very clever way that you get some nice cancellations and you get something that's even like sparse.
Yeah. So FSTX can be actually arbitrary.
Right, these are arbitrary polynomials. I just require that the whole sum is non-zero,
Yeah.
right? So like there could be really strange cancellations happening. Yeah. Okay, so that's the plan of the proof. Any other questions? Okay, so let me just leave you with a couple of open problems. So if you were at Newton's course earlier this morning, you would know that this is the obvious question to ask is, what about positive characters? Right, I was working over the field of complex numbers, partially because this only works in characteristic zero. Right, so if you want to do something like this over a finite field, the proof breaks. I need to divide by large numbers at some point, and I can't rule out that I'm not dividing by zero in characteristic P. So it would be interesting to do something like this in positive characteristic. Another question that I think is interesting is this dichotomy between matrix multiplication and PIT. Like on the one hand, we're talking about whether or not omega is 2. That's a very strong like algorithmic result. On the other hand, the polynomial identity testing algorithm, we're talking about, you know, brute force exponential time versus something that's still exponential time, but better than brute force. And it feels like maybe that's a weak kind of connection. It would be really, really cool to say that either omega is 2 or PIT is in polynomial time. Right? That would be an amazing result. And there are these sort of bootstrapping and magnification results in algebraic complexity. Bootstrapping says if I have some non-trivial PIT algorithm, I can actually take that and recursively improve on it to get a polynomial time algorithm. But you need some special structure in the starting algorithm that we don't have here. This magnification says, if I prove a non-trivial lower bound, I can actually prove a super polynomial lower bound. Right? If I prove maybe an n to the 5 lower bound, I get an n to the log n lower bound for 3. Right? So maybe you could take the lower bound from matrix multiplication, magnify it to something stronger, and then use known hardness versus randomness results. I think that would be interesting. And then finally, I mentioned there is a gap between what this obtains unconditionally and what you could hope to obtain without proving new circuit lower bounds. And so, it seems like an interesting question. Can we use this Bauer-Strassen lower bound to design new algorithms for PIT? I don't know how to do this. I don't have a great idea of how to do this, but I think it's an interesting thing to think about. So that's all I wanted to say for now. So thanks all for coming and for your attention.
Questions? More questions, or from the internet or from the room?
Yeah.
So your generator uses single matrix multiplication.
Yes.
Right?
Yes.
So is it possible that you would get a stronger generator if you use exponentiation or something like this?
So what do you mean exponentiation? Like maybe?
Well, I don't know. Instead of just looking at the matrix product, look at the matrix product for some power. Say that it might be a bit more random.
Maybe, I don't know. I haven't thought about that. The reason I use this generator is just I know exactly what it fails to hit, and so I can just prove a very nice lower bound there. If you're using powers of it, you might just have to show a lower bound for powers of these polynomials that I'm talking about. I'm not too sure about that though.
So how much of a problem is this positive characteristic? Is it like a major roadblock, or is it more like?
So at some point, I really want to divide by like some arbitrary natural numbers that are non-zero. And I just don't know how to not do that. And in particular, like the sort of adversary that you're fighting, could pick, some numbers where whatever characteristic you're working over, like that number becomes zero. You really have to divide by that number. So it just seems like I have no good idea for it. You can, in positive characteristic, you can get something quadratically worse than this, but you lose this really tight connection between PIT and matrix multiplication. So you can do something, but it's like the parameters aren't nearly as good.
Any other questions?
Andrew,
Yes.
at the beginning, you didn't tell us what is your opinion about W is 2 or not. And
So I believe I'm not well informed enough to have an opinion on that. Maybe to be contrarian, I'll say it's not 2.
okay.
Because then this result is stronger. The derandomization is stronger. So.
But connecting back to what we talked about over lunch, like polynomial identity testing is doable in polynomial time, like that.
Oh, that should be true.
Okay.
That should be true. But like, well, why it's true, I don't know. That's what we're trying to figure out. Yeah.
Good. So let's thank Robert again. So we are back after the break, and now Robert has promised to, all sensitive viewers have left the room, and now we'll see all the gory details.
Yes. So as far as details, so this is the proof sketch that I mentioned on the final slide of the first part of the talk. So the first implication, this Bauer-Strassen thing, this is about 40 years old. I don't want to talk about it. This result by myself and Michael, well, that's, as far as this work is concerned, that's something we're just citing. We're using that as a black box. You don't need to understand how that work is actually, how that's proved in order to use the results. And you use it in a fairly simple way. So what I'm going to focus on in this technical part is really this new contribution, which is how do you capture this trace of matrix product as a product of determinants. So How do you do that?
But okay, so an extremely stupid question. Like if you zoom back.
Yeah.
Yeah. So the punchline of this was this like what happens when we get all of this, that we rule out this box in your worldview? Or,
So what happens when you get all of this?
I feel I lost.
Yeah. So what happens is, let's say you get this.
Yeah.
Then this lower bound on omega means that everything that vanishes on our generator must take a somewhat large circuit, at least like r to the 2.1. So
Yes.
the point is, where does our circuit fail? It doesn't fail on linear size. Or where does our generator fail? It doesn't fail on very small circuits. You need at least n to the 1 plus delta size circuits before the generator starts to fail. Right? That's what this gives you. Right? And then if you have the generator, you use this very standard recipe to get an algorithm for polynomial identity testing. Okay, so all I want to prove is that the bad examples for the generator are not trivially easy to compute. They take some effort to compute. Okay.
Could you give us some intuition for the last implication, the third one? Like, it just seems coming very much from above to me that these determinants are somehow the bottleneck here.
Cheeky answer is no, I can't give you intuition, because to me it also feels like it's coming from above.
Can you lie convincingly?
Yeah, so I can try to lie convincingly. So let me go back to what those polynomials look like. So this is the one problem with using transitions. Okay, so we're looking at polynomials like this, and I want to show that if I have something like this, then I can efficiently turn it into one of those determinants that I spoke about. What is this? This is like some sum of multiples of determinants. And you can actually write this as a sum of products of determinants, right? So every variable is a 1-by-1 determinant, but there is also a more interesting way to write this as a sum of products of determinants. Okay.
Okay, but as Nusser pointed out earlier, f could be like a permanent, for instance.
Yeah.
So wouldn't that somehow, wouldn't then you have something very difficult in there?
Oh yeah, but I can use the permanent, like I can take projections of the permanent and get determinant, right? The permanent is computationally very powerful, right? So all I'm saying is that this sum, like I'm starting with these determinants, which are computationally powerful polynomials. When you take this, you take these multiples and then you sum, maybe there are cancellations that give you something that's a much weaker polynomial. And I'm saying that somehow you're still preserving the computational power of the determinant when you do this sum. Okay. How you end up proving this result is something like you have all these different determinants that you're looking at. So what you're going to do is you're going to do a bunch of row and column operations on the matrix of variables. So what I do is I take some multiple of the first row and add it into the last row. I take a different multiple of the second row, add it to the last row. Take some multiples of all these first n-1 rows, put that in the last row. Okay. Put that last row aside. Again, new weights. I take a multiple of the first row, add that to the n-1 row, keep doing this, right? And so I'm doing some kind of like weighted sum. And if I set the weights correctly, I kind of isolate only one of these determinants. Okay. And I do that with the rows, and then you also do that with the columns.
Is it possible to explain this thing via an identity that we typically use or something? Like
I'm not sure. There should be a way.
Because like, for example, your ISO looks a bit like this, right? You add a bunch of rows and then you multiply them and do something or the other. I mean, it's not really doing that.
It looks like Cauchy Binet.
That's what I was thinking.
But it's not really.
No,
it's not exactly.
It's not like Cauchy. Yeah, I wish I had a better explanation for this.
Yeah.
Sure,
But
sure.
I'd be happy to tell you later more details about how that proof works, and maybe you can see something that I'm still not seeing.
That's why I should say it looks a little bit similar to the North. No, that
Right. Yeah.
Precisely. This is where you throw it in, right?
I didn't fail. Yeah.
Yeah. So I won't talk about this, but I can talk about this more later.
Sure.
I see. But I think your explanation definitely helped me in that I realized that, I mean, you just need to show hardness for this and then you get hardness for that.
Right.
Yeah, I was somehow thinking of some sort of equivalence and then I was confused for like a permanent.
Oh, no.
So you're just showing that it's enough to show hardness for this and then you get.
Right. So this is kind of a normal form.
Yeah.
Right. The sum that we were looking at earlier was like highly unstructured because there could be permanence or even something worse.
Yeah.
But I at least can reason about determinants, and I also know where all these determinants are coming from. They're upper left set matrices.
Yeah, thanks a lot.
Mhm.
That's helped a lot.
Okay.
So again, the punchline of this slide is that you have decided that you have this n by square root n by r times r by square root n matrix multiplication. This is your G,
Mhm.
and you're plugging this in
To a small circuit.
to to some F thingy.
Yeah, into some F that's computed by a small circuit.
Yes.
And F could vanish on that matrix product you plugged in. Right? And what this is going to prove is if F vanishes on the matrix product,
then it
then-
couldn't have been that small.
it couldn't have been that small. It had to be at least a little bit large, the circuit.
Okay.
Okay.
So then what pops out like it's a lower bound for
So
F.
yeah, so it's a lower bound for F. So then what you can do is you can take R to be somewhat less than square root n.
Mhm.
And you set R so that whatever size circuit you're testing, you set R just large enough that this lower bound is larger than the size of circuit you're testing, but not too large that this square root n times R should still be less than n.
Mhm.
So like here, if I'm testing a circuit of size order n, I would set R to be something like n to the 0.49. Right? So the seed length of the generator is like n to the 0.99, and the lower bound is still good enough. Or sorry, I would set R to be n to the 0.49, not 0.99.
Yeah.
Yeah.
I think that's
Yeah, I think
Yeah, okay.
that's what you said.
Mm.
So that's
Oh,
fine.
sorry.
initially-
The coffee hasn't hit me yet. So I just want to talk about somehow putting this trace of matrix product inside these products of determinants. So here's this trace of matrix product polynomial written out. These are R by R matrices, and it's just this sum over ij and k. You have xij times yjk times zki. That's the definition. And I want to interpret this in a graphical way. Okay, and if you know the word ABP, this is going to be an ABP. Well, almost. So I'm going to draw a graph. It's a 4-part type graph. So it has 4 parts. They're arranged in layers. And each layer has R vertices. I'm going to draw some edges. I'm going to, from vertex I in the first layer to vertex J in the second layer, I draw an edge and I label it with the variable xij. From J to K in the second layer, from J in the second layer to K in the third layer, I draw an edge and I label it with the corresponding Y variable. And for the edges from layer 3 to 4, again, I draw an edge and I label it with the Z variable. Now, notice that if I take a path from I in layer 1 to I in layer 4, and I look at the edge labels that I see, the product of those edge labels is exactly one of the terms in this trace. So there's a different way to think of this trace. I sum over all values of I, and I look at all the paths that go from vertex I in the first layer to vertex I in the final layer, and I take the product of the edge labels appearing on that path. And that is this trace. That is exactly what this trace is. Now, why am I telling you, why draw this graph? Like, what is this going to give us? Well, this will help us. We're going to do something to this graph where we end up having a nice somehow this graphical view is going to help us build the determinants that we want, right? Build the matrix that we're going to take determinants of and somehow get this trace. So let me tell you what we're going to do. So a bit of a digression. So I have a directed graph G. A cycle cover in this graph is just a vertex disjoint collection of cycles. So for example, here's a cycle cover in this graph. All these highlighted edges, they're vertex disjoint. Oh, and these cycles should span the vertices. I forgot to write that, but they should definitely span the vertices. Why are cycle covers in directed graphs interesting? Well, if you take the weighted adjacency matrix of this graph, so in the ij entry, I put the weight of the edge from I to j, and you look at the determinant of that matrix, what does it compute? It's a sum over all cycle covers of the product of the edge weights in that cycle cover, but with some sign. And this sign is just counting the number of even cycles in that cycle cover. Okay. Now, why is this? Well, if you just think about what is the determinant of A, you have one term for every permutation of the vertices. The permutation induces a cycle cover. And well, what are the terms? It's all the edge weights. You're taking a product of the edge weights in that cycle cover, right? So this is exactly the determinant of this adjacency matrix. So why tell you about this? Well, I have at the top a graphical interpretation of this trace. And at the bottom, I know something about, taking determinants of adjacency matrices of graphs. So there's something here, but we need to glue things together appropriately. So what are we going to do? We're going to modify the graph so that we get this trace by taking the determinant of the adjacency matrix. Well, almost. So here's what we're going to do. So here's our graph. So I'm going to draw an edge from vertex I in the final layer to vertex I in the first layer. And I'm going to add self-loops to every vertex. Okay. Now, what does a cycle cover look like in this graph? Well, one cycle cover is I take all the self-loops. Okay, that's not interesting, but it's there. What's another cycle cover? Well, I could take this cycle that I've drawn here, right, where I go from I to j to k to I back to I. That's one cycle, and then I take the remaining self-loops. What would the product of those edge labels be? Well, it's one of the terms in the trace. But there's something bad here. We could find other cycles too. So for example, there's this red cycle where I start at I, and I go to some vertex in the final layer that's not I. I take the backwards edge, I meander back to I in the last layer, and then I go back around to I. And then take the self-loops as the remaining cycles in this cycle cover.
Oh, so you want directed from left to right?
All these edges are directed left to right, but these edges are from layer 4 to 1.
There is an edge from last I to the first I. So for that,
Yeah, so this edge is directed from here to here.
But also, like, if you had several paths from I to I, like, you'd like to pick up all of them now?
Right. So what kinds of cycle covers do we get in this graph? So,
but you could just add a source and a sink and fix this problem. Like there's a unique source and a unique sink, then a cycle cover must pass through this. You can't repeat it.
Yeah, but it still will forget where it came from.
yeah, so that's the problem. I need to remember that I started at I and I'm ending at.
Okay, sure.
That's if
I get it.
Yeah. So we need to, like, we're almost there, but the problem is we need to rule out these cycle covers that use multiple edges going backwards, right? I only want to use at most one backwards edge in all my cycle covers.
Yeah.
Oh wait, you're going to sum over all the cycle.
Yes. So if I take the determinant, it has to sum over all the cycle covers. But I'm picking up all these bad terms that use multiple backwards edges. Those don't correspond to terms in this trace of matrix product. Those are erroneous. I want to ignore them somehow.
Yeah.
Okay. So how are we going to do that?
The pinball trick.
No.
And do interpolation and just look at linear coefficient.
Shouldn't have advertised it.
Well, okay, yeah, you solved it.
So it is the Van Oort trick, and you
Oh, well,
extract
but-
the linear
but-
homogeneous component.
But I don't want to do interpolation.
Okay.
I'm going to do it
Fair
without interpolation.
Okay.
But you add like edge weight for
Mhm.
the reverse edges? I don't know.
Yeah, so label the reverse edges with a weight epsilon.
Damn it. Good one.
Yeah.
So
So
you get epsilon squares for the bad guys.
yeah.
Or higher
So
powers.
okay. So think of epsilon as a very small positive real number.
Mhm.
Okay, and expand this determinant as a polynomial in epsilon. Okay, well, you get for every power of epsilon, you get some polynomial in x, y, and z. And the point is, what is this ith term here? It corresponds to the cycle covers that use I of the backwards edges.
Mhm.
Right? So I'm counting how many backwards edges I use. So this is what you get. You get that the determinant of this matrix is 1 plus epsilon times the trace plus some higher order junk.
The one is because of the self loops.
The 1 is because of the self loops.
Yeah.
The linear term is because we're using exactly one backwards edge. So we've really just got, this path that starts and ends in the same part. And then I've got junk. If you're really paying attention, you'll notice that this should be a minus, but doesn't matter. Let's multiply all of these edge weights by -1 and fine. It's
Or
easier.
just add extra vertex going back further back.
Yeah, exactly. Just carrying around like -1.
Can you show, like, why was this determinant what we want, like probably 3 slides back or 2 slides back?
Yeah. So, here, let's go to this.
Whoops. Okay.
Yeah. So what is one of the monomials in the determinant? It's described by a permutation of the vertices. Now that permutation, you can decompose it into cycles. Right. So let's look at one of those cycles. What's going on in that corresponding term of the determinant? Well, you have the x sub I comma wherever that permutation sends I. So say it sends I to j, you pick up the weight of the I to j edge. You're doing this for all the edges in that cycle cover. So it turns out that the determinant of this adjacency matrix is some signed sum of the products of the weights on these cycle covers.
Are we assuming that we have self loops everywhere now, or we don't?
No assumptions about self loops.
Okay.
But in the graph that he creates, there are self loops on every vertex.
Yes. So in the particular graph we look at, there will be self loops.
Okay, but now you wanted to connect this to the trace.
Right. So we build this graph.
No, you skip by the.
Oh. Right. So the point is we have one graphical interpretation of the trace, but it's the sum over paths that start and end at the same vertex. Well, if it starts at I, it should end at I. Right? It should remember where it came from.
Yeah.
So Robert, just to clarify that this picture is not just one path, right? It's this whole blob of paths that start from I and end at I.
Exactly.
It's like this cloud of.
There are so many edges here, but I didn't want to draw them.
Yeah, sure. But it's just to understand, it's like this.
Yes.
Yeah, and for each eye, there is this one thing, like
right.
like this.
So there could be a path that goes like up here, down here, there.
No, sure.
Right.
Okay, so that's the single. That's one of the many monomials. That's a sum of some monomials that correspond with I and I.
Yes.
Yeah, there are like whatever n to the 4 of them. Or something.
Yeah.
And
some large number.
Yeah, large number. Sure. Yeah.
So he has access to all the cycle covers, but with these negative weights.
What I don't understand is, like, say from I to I, you have like 100,000 different paths from I to I.
Yeah.
And from I minus 1 to I minus 1, there's just a single like path. And then like in the cycle covers, like you're going to pick up this one cycle over and over again, but from I to I, you're somehow going to split over these 100,000 different cycles.
I mean, every
Like
such path can be extended to a cycle cover by just going back to the start and then padding the set loops everywhere else.
Oh,
He wants to isolate these special cycle covers that are paddings of one single path.
Right.
That's
so
that's
so I want the cycle covers that look like this.
Like every path can be extended to a cycle cover by the back edge and then this array of set loops.
Oh, now I finally
And now
get
these
it.
are the good ones. You want to isolate the good ones from the entire set of cycle covers, of which there could be others that just do this. Oh,
No,
perfect.
yeah, but that's like, no, but another, yeah.
Like every three path will be counted as an extension of the cycle.
Yeah,
cover
but
plus
another,
spread.
but this was somehow, okay, I guess what I didn't get, this is somehow clearly invalid, right? This is
Yeah,
like
this
fake.
is invalid. Yeah.
Yeah,
Right.
but another bad one that you're also filtering out is like, you know, a perfectly valid cycle from I to I, and then a perfectly valid cycle from R to R
Yes,
that are
yes.
disjoint. Those
Yeah.
you also want to
Yeah,
filter
Yes,
out.
those
two
you
bad
also
examples
want.
as well.
Yeah, but this I didn't understand. But
Okay.
you're saying,
Yeah,
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 true.
Yes, yes.
Perfect.
because they didn't seem fake to me, and they're still bad for us.
Right, they're
Yeah.
still bad. They're still bad. So I really only want to use one
Okay,
of these back edges.
I think I got it.
And
Thanks.
the point is, now using this interpretation, it should be clear that this determinant is 1 plus, well, the linear term is the trace. And then you have this extra junk. And like Radu said, you can do interpolation. You could interpolate with respect to epsilon and pull this out.
Yeah.
But this is a potentially large degree polynomial. You might need to use many evaluations. And I want the reduction to be really efficient. So I really only want to use like this one determinant. I don't want to have to evaluate it many times. So how do we do that? Well, the obvious thing is you solve the equation for trace. Okay, and if you take the previous equation, rearrange it, you see that if you take determinant of the adjacency matrix, subtract 1, divide by epsilon, and then take the limit as epsilon goes to 0, get the trace. So this lets me compute this trace of matrix product. Okay, it's not an exact computation, but it's a computation in the limit. That's okay, because we're talking about computation in the limit anyways. We're talking about border rank. And I've hidden this the whole time, but border rank is about this kind of computation in the limit. So this is part of the reason we're talking about border rank, is I only know how to do this in the limit. I don't know how to do this exactly. And I would conjecture that maybe doing this exactly requires a little bit more effort.
I think there's this general distinction between trace and path ABPs.
Yes.
Some literature on that, where precisely this kind of distinction plays a role.
Right.
So it's just a keyword that maybe
Yeah.
has in some way.
I
Right.
would even assume that there are like gadgets to kind of filter out this even.
Mm-hmm.
I mean, the single S, single T is not quite flying, but
Something non-trivial needs to happen there, because you can, with a simple DP, count, for instance, paths that go from I to J in a
Yeah.
graph of any length. But counting cycles needs n to the omega somehow. So this one thing is really linear time, as in n square. If you have a dense graph. And the other thing requires matrix multiplication. So the other thing being you enforce it, you go back to the start vertex. So just
but if we
fine
believe
grained
that the
complexity.
matrix multiplication is n squared, then I don't see the major gap there. Yeah, I mean, I don't know.
Yeah, I mean, for linear, like for sparse graphs, it would still be a difference.
Okay, after.
Yeah.
Okay, anyway, sorry.
No.
Derailed
But
this.
yeah, so this is, at least if you just have one determinant, you can get this trace. But I told you that we're looking at products of powers of determinants. So what happens? Okay, so just to recap, we got the trace out of a single determinant, and these are R by R matrices, and we only needed a determinant of 4 times as large size, right? So this is a really efficient reduction, like linear time. But we need to reduce to all the polynomials that look like this. And I claim that almost the same reduction is going to work because of the magic of this sort of border computation. So let's look at a simple example. Let's look at what happens for a power of the determinant. Okay. So we saw earlier that if I take the determinant of this adjacency matrix, it's 1 plus epsilon times trace plus some junk. Now what happens if I raise that to the power, some power A? Well, you get a 1. What happens to the terms that are linear in epsilon? You get a of them, right? And then you get the higher order junk. So somehow, the fact that we're putting the trace in this very low degree term, we kind of just get these, we can handle these powers for free, right? Because now to compute the trace, I just take this determinant, this power of a determinant, and divide it, instead of by epsilon, I divide it by epsilon times a. And then I take the limit. So this is how you handle powers. What about determinants of upper left submatrices? That gets a little more interesting, but I claim it's not too hard. You just need to understand the cycle cover. What are the cycle covers in the corresponding graph? So let's look at this adjacency matrix. I take the adjacency matrix and I just throw out the final row and the final column. Now I need to tell you what that means in the graph. So I'm going to order the adjacency matrix so that the last R rows and the last R columns correspond to the vertices in the final layer of the graph. Okay, so if I throw out the last row and column, that's like throwing out that final vertex. So what am I computing? Well, again, I'm computing the sum over cycle covers, but now I'm dropping all the cycle covers that start at R and end at R. Right? I don't have those anymore because I've dropped that vertex. So what is this determinant? Well, it's 1 plus epsilon times the trace, but a trace of a submatrix of the product, plus some higher order junk. That's not too bad, because we're still getting a trace. So now I claim that we actually have enough to just understand how this product behaves.
Could you just explain this last part again?
Yeah.
Somehow zoning out.
No, that's totally fine. So I throw out this final vertex, right? And now what are the cycle covers in this graph that use at most one backward edge? Well, if I start from I and go to I and then use a backwards edge, that's still there, right? There's the all self loops cycle cover. There are all these junk cycle covers that use multiple backwards edges, but I cannot go from R to R and use a backwards edge now, because that vertex is deleted.
Yeah. Okay.
Right. So what are those terms that use one backwards edge? They're all they correspond to the paths that start at some vertex between 1 and R minus 1. They start at this, say R minus 1, go to R minus 1, and then loop back.
Okay.
Right. So you get a trace of a submatrix.
Okay. Okay.
Of the
Is it important that you just delete one of the 4 vertices, or?
No. So it's
I mean.
So it's not so important that I deleted like just one here. I could have deleted 2 or 3 or half of them.
Yeah.
Right. And you'll get the linear term will be a trace of some smaller and smaller submatrix of the product.
Okay.
Right. So the fact that this minus 1 and this minus 1 are the same. If this was minus k, then this would be minus k.
Okay.
Right. So at this point, we actually have enough to just understand this entire product of powers of determinants.
Sorry, but if the R minus 1 was R minus 2, which guys would disappear?
These 2 would disappear.
Okay, only the last column.
Right. So I order the adjacency matrix. So the last R rows and R columns correspond to this part of the graph.
Yeah. And I think my question was just like, is it important somehow that you just delete one vertex per vertex that you delete on the left, or would it also be okay if you just delete the entire row?
Sure. I mean, you can delete the entire row, but so if I delete, for example, instead of this vertex in the bottom right, I delete one of the intermediate vertices, then I still have some cycle covers that correspond to paths from R to R, but now I'm only getting some of the paths, right? I'm getting all the paths that might avoid this intermediate vertex.
But can you jump?
What do you mean jump?
So you could go to a layer above and come down, right? I mean, you start at the bottom, and then suppose the second to last you avoid it, delete it.
Oh
and
yes,
you just
yes,
go
of
up
course,
and,
of course.
Yeah.
Okay. I mean, deleting the entire row.
Entire.
Oh, sure. You could delete the entire row, and
Then it's gone, and we don't have to argue.
right. But at least formally, like when I'm looking at this adjacency matrix, I'm only deleting that single vertex.
Okay, got it.
But it has the effect of deleting the row.
Yeah, that's right.
So this I don't see, but maybe it's not so.
It just seems that it's not that important.
Okay, maybe
That it's
not so
whether it's
important.
1 or 4 that you delete.
Yeah, it's important that it's either the first or the last.
Yeah, so that the cycle is not completed.
Right, exactly. You're not allowed to complete the cycle. And one other thing I'll mention is if you've deleted this entire final column, then the determinant of the adjacency matrix is 1. Because
Self-loops.
you only can use the self loops. There are no other cycles in the graph. Okay. So that actually already takes care of the small determinants in our product. Right? Once the determinants are small enough, they're all 1. And well, 1 times something is something. So how do we handle this product? Well, it's like I said, you ignore all of the terms that are smaller in there, that are of size 3r or smaller. Because once you hit size 3r, you've deleted all r vertices in the final column. So you only have subgroups. Okay.
Weird. Yeah. Nice. Nice.
So then what are the other terms you pick up? Okay, so for the ith term in this product, you get 1 plus the linear term is this trace of a submatrix of the product plus some junk raised to some power. Okay. So the first thing is, well, we saw that powers are easy. They like linearize in a nice way. So when you take this power of this term, well, you get 1. The linear term is just multiplied by the power. And then you have higher order junk. And the higher order junk is different in this line from this line, but it's still junk. I don't care about it. Now I've got this product. Well, the constant term is still going to be 1. What's the linear term? We can figure that out. So it turns out that the linear term is the following thing. So, well, right. The linear term in the full product is just the sum of the linear terms in each of the factors. Right? So I'm just taking this guy, moving it down and putting a sum in front of it. And then there's higher order junk. Okay. Now, what is the trace of this submatrix? I'm summing the diagonal entries of this product from the 1, 1 entry to the II entry. Okay. You can rearrange this sum. And you end up getting this. Okay, again, constant term, higher order junk. And what's the linear term? You get the sum of the diagonal entries of this product, and the coefficient is this sum of the powers. Okay. So one way to see this is, let's think about what is the coefficient on the 1, 1 term here? The 1, 1 entry of the product appears in every term here. It appears in the matrix on the first row and column. It appears in the matrix on the first 2 rows and 2 columns, first 3 rows and 3 columns. And so the coefficient of the 1, 1 term is you add up these coefficients from 1 to r. Right? And you can figure out that this is the coefficient of the II term. So the point is, this is almost the trace of the product, but it's scaled incorrectly. Right? Okay, so I'm going to erase all this junk in the middle, and we're just going to keep this line. Okay, so we know that this is effectively the trace of the product, but it's just scaled incorrectly. So let's rescale it. So one way to do this is you take the matrix X and you scale the ith row by this quantity. Okay, and you'll notice, when you work out the details, this exactly cancels with this incorrect scaling here. And why is this okay to do? Well, I said at the very beginning, sorry, this 0 should be a 1.
This is where we care about the characteristic.
This is where you care about the characteristic, because I can't guarantee you can divide by these numbers. Right? And in particular, if you tell me the characteristic, I'll tell you a product of determinants where you can't divide by these numbers. And so like I said, this 0 should really be a 1. So every denominator here is at least 1. So I can do this division. So I get the correct scaling. I get 1 plus epsilon times trace plus higher order junk. So now you take this product of determinants, subtract 1, divide by epsilon, take the limit, you get the trace. So that's how that goes. And the point is that if you computed this product of determinants with S multiplications, you take that, you subtract 1, you divide by epsilon, which is a constant. We don't pay for that. So you can compute the trace in the same number of multiplications. Now you're just working in this limiting sense, but you're not adding multiplications. So if you have a lower bound on the number of multiplications needed for this trace, that lower bound applies to this product of determinants. And now you let the rest of the machinery work. You get the lower bound for what the generator.
You get exactly the same number, no multiplicative, additive, slack, no nothing. Is that important?
No, you could have a multiplicative slack and that would be fine.
Okay, but it just so happens that
it just so happens that it's the same. I mean, there is some slack because these are matrices of size r by r, and here I'm saying there's a determinant of size 4r by 4r.
Okay.
So like there's some multiplicative slack there going on,
okay,
but it's very, very efficient. Not really losing very much. So that's the meat. That's the new thing that's going on at a technical level in this work. So that's all I prepared. I'm happy to talk about other things, either on the whiteboard or on tablet or whatever.
Yes, sorry, 1.5 minutes now. What happened? Like the dust settles, bring us back to where
the dust
were we?
settles.
Like, so now we have.
So
maybe could you draw a picture of these implications? PIT implies this, implies like the words connecting.
Sorry.
yeah,
So thanks a lot.
yeah,
And
absolutely.
I'd be very happy to chat at some point.
Okay,
During the presentation.
absolutely. Okay. Thanks. Yeah. So the implications that we've got. Sorry, is this visible on?
No.
No. Here, maybe I can move this guy over here. Okay.
Yeah. This is and then just perfect.
Okay, great. So what are the implications? So we said omega, let's say, is 2.1. So the first implication is this Bauer-Strassen.
Actually, could you stop sharing then maybe if you're not using this, because it's now, I think it's a little bit hard to see.
Yes, is that good?
Yeah, we have some weird. Would you move the?
Oh, I'm sorry, it's not really a very.
Sorry.
No, but a little bit more clearer.
Sorry, I'm trying to find the zoom.
No. Just if you leave it alone,
Yes.
Robert, and just turn the board.
Like this? Or?
Yeah. So rotate it.
Rotate it like this.
Yeah. So you get a better something like this. I think is.
Okay.
And then you can play around with. I don't know what markers we have. This one.
Okay.
Was there another like black somewhere?
The in-person audience is not able to see.
Let's try.
Okay. So, oh, you know what? I could try hooking up my tablet and see if that works.
Or just write it.
No, it's
I'll just
fine,
write it.
yeah, it's
Okay.
small.
Don't.
Yeah. So point
Not
is,
at the very top because we don't see that. So it's slightly
Maybe
lower.
here? Is
Like
this-
yeah, that's perfect.
so first assumption, omega is 2.1.
Omega is 2.1.
So Bauer-Strassen.
And a little bit larger, I think is also helps.
Strassen says that this trace XYZ needs n to the 2.1 multiplications. Okay. what we just proved is that this says that if f vanishes.
And when you say that the trace requires so and so many multiplications, this was in this weird, like limiting
This
sense.
weird limiting sense, yeah.
Okay,
Yeah.
so
Which
getting
is
like computing a polynomial such that when I let epsilon go to 0, the right thing pops out.
Yeah.
And that's why we're allowed to play this epsilon game.
Yes. Yes. Because it turns out that you can play the epsilon game for matrix multiplication and actually get an exact algorithm that doesn't play the epsilon game.
Okay.
Okay, so what we showed is that now if f vanishes on this generator, if the generator fails, then f requires something like r to the 2.1 multiplications. Okay. So then what does this say? So if f.
Oh, and wait, and the reason for this was what's hidden there, like if f happened to vanish, then this had this very particular form that we now spent an hour analyzing, that, well, polynomials of this very peculiar form, we wrote them as traces.
We can use them to write a trace, yes. Yes, so
Okay.
if I have a polynomial of that very particular form, I can do something to it and get out a trace.
And,
and do that in an
oh, and
efficient
get
way,
out a trace without, okay, right.
without doing too much extra work.
Mhm.
So then what does this say is that, you know, for example, if, you know, C is a linear size circuit, GR hits C with R, you know, something like n to the 0.49. So what you get is, for linear size circuits, you get a generator with seed length n to the 0.99. Right? And so what that gives you, not sure, is here still okay?
Now the online audience cannot see it. You
Yeah.
have to maybe rotate your laptop a little.
Oh, sure. Maybe that?
Yes, I think.
Yes. So this final thing says that you can do PIT for linear size circuits in exponential in n to the 0.99 time. And that's the final thing you get. So that's the map.
Why did you get order n size circuits in this step?
I'm just saying I'm going to pick a size that I want to hit. And order n is easy enough to think about because it's really small and I don't have an extra exponent to distract.
Sure.
You could make this, you know, n to the 1 plus epsilon, like
Yeah.
n to the 1.0001. So the point is that this arrow, that's the new one, and everything else is like kind of a pretty easy recipe to follow. If you've been thinking about it for a while, it's an easy recipe to follow.
So again, for the, you know, for the dense persons in the audience, what this boils down to, like me, is so, you know, I'm starting with a matrix multiplication exponent that is somewhat large.
Yeah.
And that gives me a polynomial identity testing algorithm that is somewhat non-trivial.
For very small circuits.
Yeah.
Yep. And like I said, you know, if you improve on this too much, then you might prove a new circuit lower bound. Like there's some expected trade-off between the hardness assumption that you have and the amount of derandomization you can get. And this is kind of doing the thing you would expect because of that trade-off, without getting too much into the detail on that.
Okay.
All right.
Questions, comments, protests? Otherwise, I think we're.
I think we're set then, right?
Yeah, I mean, thank you, Robert, again.
Thanks for being here. And thanks for sticking through to the end.
Thank you so much.
Yeah.